Okay, so let's get started. And today we're going to finish off our discussion on diffraction. And this is a really important topic in condensed matter physics because it helps understand how we use X-rays or neutrons and even electrons to find out the internal structure of crystals. And it also accentuates or highlights the importance of the reciprocal lattice. And in the previous lecture, I already described how the concept of the reciprocal lattice unfolds itself. So a quick recap of the previous lecture before we move on. So let's get started. I share my screen. So by the way, I hope you've already seen lecture number 8, which dealt with the reciprocal lattice and the evolved construction. So are there any questions stemming from that lecture? And can anyone just explain the summary of it? What is the central idea of lecture number 8? So my question is, I have X-rays coming into a crystal in a certain direction. What determines the direction of the scattered X-rays? Any thoughts about this? Yes, Mariam.
So we use this technique where we draw a sphere called the evolved sphere, and the points, and we draw a grid. So the points that the evolved sphere touches or intersects with any other lattice points, which is our grid. And then we can say that those points are the ones where the X-rays will be scattered in those directions, along those directions.
Right. And the grid is the reciprocal lattice. It's
Yes.
not an arbitrary grid, it's the reciprocal lattice in the proper orientation. So you rotate the crystal, the reciprocal lattice tilts as well. You change the angle of incidence of the X-rays, it has to be reflected in the evolved construction. So the basic idea which you could see, let me draw the evolved construction again. So I have points which correspond to the reciprocal lattice. All right. So I draw the reciprocal lattice. Here you go. And then I draw the direction of the incident X-ray, which passes through a particular point, which I call the 1,0,0,0 point, which is the origin of my reciprocal lattice. And then I scan the surface of the evolved sphere and see whether the evolved sphere touches any other reciprocal point. So in this case, it touches a reciprocal point over here. So this means that a crystal is placed at the center of this evolved sphere, and a scattered X-rays emerges from the crystal and goes in the particular direction of the reciprocal lattice point that is intersecting with the evolved sphere. And this angle here is my 2 theta angle, and half of this will be the grazing angle or the angle of incidence for the X-rays. And I can also identify the index of this reciprocal lattice point, which will correspond to a family of planes. So this is the evolved construction. Now, if you observe from the evolved construction, only certain directions are allowed for the scattering of the X-rays. And this is a consequence, a direct consequence. We've seen from the evolved construction that this is a direct consequence of the Bragg's law. 2d sine theta is n lambda, where n is an order of diffraction. So it's a direct consequence of this. So the radius of this evolved sphere, if you recall, is 1 over lambda, and this particular vector is a reciprocal lattice vector. And there are three vectors at play in this diagram. One is the vector which corresponds to the incident X-rays, S naught. Now, consider S naught to be a unit vector which points in the direction of the incident X-ray. So, this is one vector that is at play here, S naught, the incident direction. Then we have the scattered direction. Let's call this S. So, S is the scattered direction. It's again a unit vector. And the third vector that you see is coming to life in this evolved construction is the reciprocal lattice vector, DHKL, where HKL defines the index of the reciprocal lattice point which intersects the evolved sphere. Okay. Now this means that the Bragg law involves three vectors. So what we're going to do today is basically the title of today's lecture, I would like to call it a Fourier description of diffraction. But I would like to start off by recapping the Bragg law, and I would like to present a vectorial formulation of the Bragg law. And this becomes really important in our study of solids because it helps us understand the band structure of solids and why do bands occur in the first place. So let me draw a particular construction here. So I have a plane of atoms and an X-ray comes in and there is a vector corresponding to the incident X-rays S naught, and remember it's a unit vector, and I suppose that okay, I need to redraw this because I need some more space. So let me redraw this thing over here. Here I go. Here is the plane of atoms. I draw an incident X-ray. Let's call this vector S naught. And then there is a scattered direction, which corresponds to a vector S. Angle here is theta, and so is this angle. Now, if I were to find out the change in this direction of the X-ray, so as it is scattered from the atomic plane, let's find out this vector S minus S naught. So in order to find out this vector, I would simply change the position of S naught and invert it. So minus S naught goes here. The angles are proper. This is theta and this angle here is pi minus theta. And then I add S with minus S naught and I form this vector here. Just a minute, please. Let me shut down some other. So this green vector here is S minus S naught. And this is my plane of atoms. And could you tell me what direction is S minus S naught in? Is it normal to the plane? Both S and S naught, by the way, are unit vectors. Precisely, S minus S naught is a vector that is perpendicular to the scattering plane or the reflecting plane. And we know that this vector is equal to the reciprocal lattice, as we've seen from the evolved construction. So if I were to make a triangle, which I'm now showing in thick black color here, this triangle, and this triangle, we have three sides, and the three sides are S naught, S, and S minus S naught. And S minus S naught is the vector starting from the origin of the reciprocal lattice and ending at the HKL lattice plane. So it is indeed the reciprocal lattice vector. So, and we also know from the Bragg's law that excuse me, uh, we also have seen already that S minus S naught over lambda is the planar spacing 1 over d. We've also already seen this from our previous lecture. And 1 over d, if I multiply this with 2 pi, of course I need a vector sign here. So let me just for the time being put a unit vector n, which is normal to the plane. So I have S minus S naught over lambda. Since I multiply both sides by 2 pi, I get this expression. Now, what is the vector on the right hand side equal to? What is 2 pi over d and normal to the plane? What is this vector representing? What kind of vector is this? What do we have on the right hand side of this vector equation? So we have planes with the spacing d, and we now have a vector which is normal to the plane, and the length of this vector is 2 pi over d. So what kind of vector is this? Can anyone just speak up, please? Or
A reciprocal vector?
it's a reciprocal lattice vector. So this is simply DHKL star vector. Okay. So on the right hand side, we have a reciprocal lattice vector, which is equal to the change in the scattering vector. So when X-rays are diffracted, the direction of the X-rays suffer a change. And the change in the scattering brought about by scattering, which means scattered minus the incident, is going to be equal to the reciprocal lattice vector. And this prefactor of 2 pi over lambda. So if you don't mind, let me just change my the batteries so that we can do this properly. राइट अभी समझ आ रही है अभी
Yes, sir.
ठीक है. So on the left hand side, if we were to define a vector, so can anyone is the factor 2 pi over lambda, does it sound familiar? Is the inverse of the wavelength. So does 2 pi over lambda ring a bell somehow? Have you ever seen the prefactor of 2 pi over lambda before in the modern physics class or anywhere else?
In the
Wave
diffraction?
number?
It is exactly the wave number. So, and the wave number can be represented by k. So k minus k naught, where the k is defined as 2 pi over lambda s, and k naught is defined as 2 pi over lambda s naught. S and s naught, by the way, are simply unit vectors. So the change in the wave number equals a reciprocal lattice. This is the key idea of diffraction, and this is the vectorial formulation of Bragg's law. And conventionally, reciprocal lattice vectors are also represented by the vector G. And you can put small HKL indices with it. And an arbitrary lattice vector with indices HKL is given, as you all know, by H A star plus B, sorry, plus K B star plus L C star. So the key idea here is that the change in the wave vector delta K is equal to a some reciprocal lattice vector. And only when this condition is satisfied would we be able to see a diffracted ray. And this is such an important equation. Now, let me draw another description of this. So if I were to draw a ray K naught, which represents an X ray coming in a particular direction with a certain momentum, you all know that there is a relationship between the momentum and the wave number, which is given by P equals H bar K. Then the scatter direction K is such that we can always form a vector which is given by K minus K naught. So if I were to draw K naught minus K naught, this is K naught. And this vector here, K minus K naught, must be equal to a reciprocal lattice vector. So the orientation of K is fixed, is determined by the by the Bragg condition, which means that K must equal K naught plus a G. So if K naught is fixed, which is determined by the direction of the incoming X-rays, then only those Ks are allowed which satisfy the equation that I've written here, which is nothing but the Bragg's law. And by the way, also remember that the magnitude of K is assumed to be the same as the magnitude of K naught, which means that upon scattering, we are already assuming that we have an elastic process. There is no change in the wavelength or the frequency of X-rays, no change in the momentum. So if this condition is satisfied, the elastic process would result in a scattering angle such that this equation number 1 is always satisfied. And this is such an important equation in all of diffraction and condensed matter physics that it's almost the holy grail of solid state. So, and by the way, if you look at the diagram that I've drawn over here, look at this diagram, I can form a plane. So I can form this plane here. And the tip of the vector K naught touches the tip of the vector K. And if I were to, so if these lengths are always the same, the length of K is always the same as the length of K naught. So I can draw a plane which becomes a perpendicular bisector of K and K naught. Now, another way to look at this is the following. If I look at equation number 1 and square both sides, I get K square equals K naught square plus G square, which is the magnitude squared of the reciprocal of a reciprocal lattice vector, plus 2 K naught dot product with G. Now you can always, so G is this particular direction here, remember, from the Bragg's formula. So if I were to look at the equation that I've written in blue here at the bottom, k square is equal to k naught square. So this would result in k naught dot product on G, which is the projection of k naught on G. This must equal to minus 1/2 of G square. This is another way of writing the Bragg's formula, which means that if I were to take the projection of k naught on G, so the projection of k naught on G can be computed as follows. So I first draw minus G, which is this particular vector here, and then I draw the projection of k naught on minus G. Then this should be equal to half of the length squared of G, which means that the length that I'm highlighting in orange, which is the projection of k naught on minus G, is equal to the half of the square of the length of G, which means that the projection drops onto the bisector of G or minus G. So this is the Bragg's formula, and I think this is such an important formula. Either you can remember this formula, or it's easier to remember the formula that I've written over here. Now, if you look at equation number 1, does this now the beauty of physics is that it takes a mathematical formula and goes deeper and deeper into it and reveals some other aspect or some other interpretation of a mathematical formula. Now, a nice physical interpretation of Bragg's formula is the following. If I have a particle of momentum k naught, forget about X-rays, forget about anything else. Particle of momentum k naught collides with a particle of momentum g. If momentum is to be conserved, then the new particle which comes out from the combination of k naught and g, from the conglomeration of k naught and g by the merging of these two particles, must have a momentum k. And the momentum k is the vectorial sum of the momentum k naught and g naught, because this is a process that conserves linear momentum. So this is how we generally view scattering. Scattering can be viewed as a collision process between two particles. Now, the particle k is clear, it's an X-ray photon. The particle k naught is also clear, it's an X-ray photon. But what is the particle g? Now, the trick, or I would say the custom in physics, is to associate particles with everything. Particles become excitation of quantum fields. Everything is a particle. An electron is a particle, a vibration is a particle, light is a particle. So particle is a terminology that is often used. So in this case, the reciprocal lattice is really, since the dimensionality of the reciprocal lattice is of, so if I were to look at this equation that I can write over here. So sorry, my pen somehow. K equals k naught plus g. So what are the dimensions of k and k naught? These are wave vectors. So they have dimensions of length inverse. Okay. So g must also have dimensions of length inverse. Okay. So this is the dimension of the reciprocal lattice vector. So the reciprocal lattice vector belongs to a space which is called the reciprocal space, and it is also called the momentum space because k's are proportional to momentums. And this lattice vector g can be considered to be a particle which corresponds to what is called the crystal momentum. And the alternative view of X-ray diffraction is that the particle is coming in, the particle is the photon of momentum k naught, and it is absorbing a particle corresponding to the crystal momentum of momentum g, and the two coalesce, they combine, they join up, and they form a new particle, which is another X-ray photon of momentum k, and momentum is conserved in the process. So here, this was an alternative view of diffraction. Any questions about this? I just give half a minute of silence to think about it, and it's such a majestic concept. You start off by photons, by waves. You look at the interference of waves, then you move to a particle picture. The Bragg's formula, which is innocuously simple for such a complex process. There are so many planes, but it just picks out the proper direction. That direction is determined by the Bragg's formula, which mentions that the direction is such that the new wave vector is equal to the old wave vector plus the reciprocal lattice vector. That's it. So any questions? All right, so now I would like to shift gears a little bit and talk about the Fourier description of diffraction. And in the process, I will show how different planes never ever diffract. And from these absences, or systematic absences as they are called, or the extinction of certain reflections never showing up in the diffraction pattern, we can tell what kind of Bravais lattice is it, and we can determine the space group and so on. All right, so first of all, I've already introduced the convolution of an object. I've talked in the first lecture that the crystal is a convolution of a lattice and a basis, and the basis is a function of the real space small r, and the lattice is a function of the real space r, and I get the crystal. So the basis is also called the motif, by the way. So I define a grid of points called the real lattice, the direct lattice, and stud it with and put the atoms or the motifs or the individual bases on each of those lattice points, and I generate the entire crystal structure. So this convolution is representative of repetition or sweeping, or taking some element and sweeping it across the lattice. So now what I would like to propose or argue is that the reciprocal lattice is the Fourier transform of the real lattice. Now I need to talk about Fourier transforms a little bit, but has anyone ever studied in mathematical method what a Fourier transform is? Does everyone know Fourier transforms? Or can anyone just tell me if he or she hasn't ever looked at Fourier transforms? Does everyone know what a Fourier transform is? In our SSC curriculum, we must have come across Fourier transforms in modern physics, mathematical methods, probably statistical mechanics as well. So can anyone just speak up? Just want to listen to someone.
We have
बिलाल
done it,
कहाँ पढ़े
I
थे?
guess.
कहाँ पढ़े थे Fourier transforms?
सर मैथमेटिकल मेथड्स में भी पढ़े थे, कैलकुलस 2 के कोर्स में थोड़ा बहुत किया था, और अभी भी जो हम पढ़ रहे हैं करंटली कोर्सेज क्वांटम कंप्यूटेशन उसमें भी कर रहे हैं.
ठीक है. तो if I were to, let's draw some pretty flow charts. If I were to take the lattice and find out its Fourier transform, so let me represent the Fourier transform by this letter F, and I were to take the Fourier transform of the basis, And I can also take the Fourier transform of the crystal. So there is a theorem in Fourier theory which says that if in the real space I have the convolution of two functions in the Fourier space, I would simply need to multiply the Fourier transforms. So the convolution in the real space becomes a multiplication in the Fourier space, and a convolution in the Fourier space, by the way, becomes a multiplication in the real space. Now, when we transform from one space to another, the variables change. So instead of R in the Fourier space, I get a new variable which is proportional to 1 over length, and this is actually called the K space or the reciprocal space. So I can really represent L as a function of K now, of the K vector, okay, which is proportional to 1 over the length. And in just to differentiate between the lattice and its Fourier transform, I can put a hat on top of L. So I have L hat multiplied with B hat and this must equal to the Fourier transform of the crystal. So the Fourier transform of the crystal is the Fourier transform of the lattice. So I can write this in English as well. Fourier transform of the lattice multiplied with the Fourier transform of the basis gives me the Fourier transform of the crystal. Now, all of this is in the K space or the reciprocal space. Now, in order to, what does this have to do with diffraction? Let's see. Let's see. So, if I were to find out the, yes, Mariam.
Sir, how has the convolution sign changed under the Fourier transform?
So that's a theorem called the convolution theorem. If you are living in the real space and you have two functions f and you find the convolution of this, and this transforms into the reciprocal space or the K space by taking the Fourier transform of small f, which becomes capital F, say, and the Fourier transform of small g becomes capital G, and you multiply the two functions. This is called the convolution theorem, and this can be proven. There's a proof for this. Okay. So I don't want to go into the proof for the convolution theorem, but sometimes it's easier to do multiplications. So one would prefer working in the Fourier space. So let me just now try to find out the Fourier transform of the lattice and the basis. And then I will connect it with diffraction. So let's first talk about the Fourier transform of the lattice. Now, what is the lattice? The lattice is a set of points. Let's do something really simple. In 1D, in one dimensions, a lattice can be represented by a set of Dirac delta functions. Okay, and the spacing between these functions is A. So a Dirac delta function is such that it's zero everywhere, but it just spikes at a particular point, and that's what a lattice is. A point exists nowhere, but then at a certain instance it just pops up, gives a flash, then you have a separation A, which is the lattice spacing, then you have another point. So this is a sequence of Dirac delta functions. Okay, and I'm sure you've seen Dirac delta functions in mathematical methods. So if I were to if my variable, the real space variable, instead of R I'm sorry, my pen has stopped working somehow again. So if this is my variable x, then if I were to write a mathematical form for this train of Dirac delta functions, what should I write? So how do I represent Dirac delta functions? So क्या symbol है Dirac delta function का?
So you can write either delta और bracket में उसकी वैल्यू लिख दें कि जहाँ पर आपको वो पॉइंट्स चाहिए,
क्या
और you
लिखूं
can write
मैं?
subscripts.
delta आगे क्या लिखूं?
ब्रैकेट अगर आपको चाहिए वैल्यू एट 1 तो 1
मैं
माइनस
ये जो मैंने भी the Dirac delta train that I've drawn, I need to write this function, this train of Dirac delta pulses. So what should be the argument
Sir,
of delta?
x
Yes,
minus a into n, where n
x
is the
minus
number
n,
of points.
right? Where and I come from minus infinity to plus infinity. Okay, so this is my lattice in real space. Now I need to find the Fourier transform of this. Okay, so how do I define the Fourier transform? So defining Fourier transforms is easy. So if I had a function f, I multiply the function with I kx and integrate over all of space. I will get the Fourier transform of x, and the Fourier transform will be in the k space. This is how I define Fourier transforms. All right. So, and then there are certain properties of Fourier transforms. So if I have a function, a Dirac delta function delta x, let's find the Fourier transform simply of delta x. So if I just have delta x and I multiply it with eikx from minus infinity to plus infinity, now I'm multiplying a Dirac delta function which is zero everywhere, but it's non-zero at a particular point. And that particular point is, so where is this function delta x going to be non-zero? Where does
at x
the,
equal to 0.
at x equals 0. So at x equals 0, there is going to be a peak. And if I multiply this Dirac delta function with any other function, in our case eikx, and I integrate over all of space, I get 0 everywhere, but I'm really sampling the function at x equals 0. So this is called the sampling theorem, by the way. So the product of the Dirac delta function with any other function is going to be equal to eik, and the value of x which at where the Dirac delta pulse exists, and that's 0. So the answer to this expression is 1. So the Fourier transform of a Dirac delta function this at x equals 0 is simply 1. All right, so the generally this is called the sampling theorem. So let me write down the sampling theorem. This is really useful in all of physics. The sampling theorem means that if I have a Dirac delta function delta x minus something, say a, or let's not use a, I'm using a for something else, say let me say b, and I multiply this with some function f of x, I integrate, sorry, I need to the variable of integration as well. Sorry, my pen is and this equals the value of the function where the Dirac delta is non-zero, and that is at beta. So this is called the sampling theorem, by the way. So I apply the sampling theorem to find out the Dirac delta function of a the Fourier transform of a Dirac delta function. Now, if you please excuse me, I just need to restart my Microsoft screen because this pen is giving me a lot of trouble. So just bear with me for 2 or 3 minutes. So let's get restarted here. Let me share my screen again. All right, so we were at the sampling theorem, and our goal is right now is to find out the Fourier transform of the lattice. So we've already found out the Fourier transform of a single Dirac delta function. So if I have delta x, the Fourier transform of delta x is 1. But I don't have delta x. I have a train of delta x. So I have delta x minus na, and I need to find the Fourier transform of each one of these. The Fourier transform, by the way, is linear. So if I have a sum of pulses, I can find the sum of all the Fourier transforms. So now there's another theorem in Fourier theory which is called the shift theorem. The shift theorem means that if I had a function small f and I find the Fourier transform of it, I will get some, say, capital F hat k. If I were to replace x with minus beta and I find the Fourier transform of x minus beta, then this would simply be the original Fourier transform multiplied with minus iota k beta. And you can prove this simply by looking at the definition of the Fourier transform. So you can prove this using this definition. Probably I give this as a homework. So if I translate the function by b units, it is tantamount to it is the same effect as multiplying the Fourier transform by an exponential function. Okay, so now if I were to find the Fourier transform of the shifted Dirac delta function, the Dirac delta function that I've drawn over here, delta x, is simply non-zero at x equals 0, and the Dirac delta function x minus na is a Dirac delta peak at a position na instead of x equals 0. Okay, so if I were to use the shift theorem and find the Fourier transform of this shifted Dirac delta function, I will simply get e raised to power minus iota k na. Okay, so k multiplied with the amount of shift, which is na, in keeping with the shift theorem. So now the Fourier transform of my lattice, the sum of all the Dirac delta functions, if I were to take the Fourier transform of this one-dimensional lattice, this would simply be equal to e raised to power minus iota k n a, where n goes from minus infinity to plus infinity. Okay, so this is the Fourier transform of the lattice. Now we can represent the Fourier transform of the lattice in another simpler way. So remember that the Fourier transform of the direct lattice, which is some function in the k space, now the x's have gone away and we have this variable k. Only k survives. So now we have a function living in the k space, which is also called the reciprocal space. Okay, so now we have a sum of exponents in the reciprocal space, which is the Fourier transform of the lattice in the direct space. Now there's an alternative way of representing this. Okay, and let me describe what that alternative way is. Now there's a lot of maths in today's lecture because of course maths is the holy grail upon which all of this rests. So now I would like to rewrite this function as a Fourier series. Okay. Now how do we do that? It's does everyone know what a Fourier series is? Are you familiar with Fourier series? What is a Fourier series? Anyone? So I think this is really important. We all need to know what Fourier series are. कोई मुझे बता सकता है in simple words what is a Fourier series and how does it work? Anyone? क्या होता है
सर
Fourier?
एक पीरियोडिक फंक्शन की एक्सपेंशन को कहते हैं फोरियर सीरीज with some weight attached to it.
Exactly. So I have so let me draw this graphically. If I had some function la 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 like this. This is my x and there's a certain period associated with it. Let's call it p. And this is a periodic function. Let's call this function small fx. Then this fx can always be expanded as a sum of exponents or a sum of sines and cosines. And how could we do that? We could write this fx as some coefficient fm e raised to power minus I 2 pi m x divided by the period p, and m goes from 0 to infinity. Okay, so this is the Fourier series expansion of a function. Okay, and fm, these are called the Fourier coefficients. Any periodic function, and this was the genius of this French mathematician Fourier, who proposed that any periodic function could be written as a sum of exponents, and each exponent is defined by a number m, and the exponent is e raised to minus I 2 pi m x over p. So this you must have learned in your mathematical methods course. Now, if I had a train of Dirac delta functions, suppose delta x minus na. Some days are just bad days for my technology. Anyway, so if I have this Dirac delta function, a train of the Dirac delta functions, first question, is this a periodic function?
Yes, sir.
It is a periodic function. By the way, let me complete my discussion of the Fourier series. So the function small f can be written as in the form that I've written in orange, where the Fourier coefficient fm can also be determined. And how do we determine the Fourier coefficient? I determine the Fourier coefficient by taking fx and multiplying it with e plus I 2 pi m x over p integral with respect to x, going from half of the period negative to plus half of the period and dividing by the period p. This is how I can determine the Fourier coefficients. So the Fourier coefficients in a sense are the inverse Fourier transform, but nevertheless. So these are my definitions. So number 2 is how I define a Fourier series, and number 3 is how I determine the Fourier coefficients given a periodic function. Now let's look at our periodic function, which is the Dirac delta pulse. It's also called a Shaw function in electrical engineering, but never mind. So I have this. So what's the period of this pulse? It's A. Now, if I would like to map this to the Fourier series using equation number 2, changing the screen size a bit, m, some fm, which is yet to be determined, e minus I 2 pi m x over the period. What's the period in the real space? Let's use p here for the time being. Let's use p. Okay, it's p. So I get p over here. Okay. So this is my equation number 4. Now, really, all Fourier expansions are the same because every one of them has this exponential term. The only difference in the Fourier coefficients. The expansion only determines the Fourier coefficients. So if I were to find out the Fourier coefficients Fm for the Dirac delta function, the Fm's are equal to, now I use equation number 3, 1 over e minus p by 2 dx. My function is now delta x minus np with a summation. So let's bring the summation sign outside. E plus I 2 pi m x over p. All right, so this is my, now what I would like to do is the following. So now how do I solve this integral?
Sum of sines or cosines depending on the f used.
No, I mean, can't I use the sampling theorem here? I have a Dirac delta function. So this is my Dirac delta function and is being multiplied by some other function. And I'm looking at only the interval minus p by 2 and p by 2. So I have this Dirac delta train of pulses. This is my x. This is my x equals 0. This is my x equals p. This is 2p, 3p. This is my minus p and minus 2p. So this is my function whose Fourier expansion I'm seeking to find. Look at this thing. This thing is drawn over here. And I'm only integrating from minus pi by 2 to plus pi by 2. So I'm integrating from this range to this range. Okay. And there's a Dirac delta function that lies inside this range. And that is this particular function. Oh, sorry. I'm sorry. So I'm sorry. So this is my range from minus p by 2 to plus p by 2. Forget the green thing. So this is my function and I'm integrating from minus p by 2 to p by 2. And inside this function, I only have a Dirac delta function. My pen, I'm just getting slightly worried about I have a Dirac delta function over here. And if I were to use the sampling theorem, and this is non-zero, by the way, only at x equals 0. So if I were to compute this integral, what would the answer become? What would be my answer?
Sum f of p, yani e I 2 pi m.
x की क्या वैल्यू आएगी? यहाँ x की क्या वैल्यू डालनी पड़ेगी? This
I
function
think
is
equal to np.
nahi. I'm integrating in a certain range from minus p by 2 to p by 2, and inside this range, a single Dirac delta peak exists at x equals 0, precisely x equals 0. So this integral here will be simply equal to e I 2 pi m x becomes equal to 0 over p. And the integral sign vanishes. And I don't need to consider any other n because my limit of integration is simply what I've shown in blue over here. Okay. Everywhere else, I just don't care. So this would be my answer for the integral. This is my fm. Okay.
लेकिन इसमें जब
Hmm?
हम डायरेक्ट डेल्टा फंक्शन में जो हमने ऊपर लिखा हुआ है जिसको आपने अंडरलाइन किया हुआ है ऑरेंज से, उसमें अगर हम x इज इक्वल टू 0 पुट करते हैं तो वी गेट माइनस p इनसाइड देयर. तो डायरेक्ट डेल्टा फंक्शन जो है वो हमें वैल्यू 0 पे नहीं देता.
नहीं, डेल्टा x माइनस एन पी का क्या मतलब है? डेल्टा x माइनस एन पी का ये मतलब है, इस फंक्शन का ये मतलब है, the Dirac delta function at delta 0 plus a Dirac delta function at so there's a delta x, sorry, this is delta x, there's a delta x minus p plus delta, sorry, delta x minus 2p plus delta x minus 3p, okay, and so on. And likewise, I have the positive signs as well. Okay. So what is this delta x? Delta x means a Dirac delta function at x equals 0. This is how we define Dirac delta function. When the argument as a whole becomes equal to 0, that's where the function, the peak exists. Okay. So now if I use the sampling theorem here, I only need to choose, I sample the function, the exponential function at x equals 0 only because of the limits of the integration. And my final result would become equal to what this is my final Fourier coefficient, which is simply equal to 1 over p, because the exponent of 0 is 1. So I can express my, coming back to the Fourier expansion of my train of pulses here, this thing, look at equation number 4. I have fm equals 1 over p all the time. That's it. Okay. And so I just simply replace f over m by 1 over p because I've now found out the Fourier coefficients. Okay. So my train of pulses delta x minus np summation over all n is 1 over p sum of minus I 2 pi m x over p, because now I found out the Fourier coefficients and each one of them is equal to p. So I take p to the other side. So, okay, let me shut down a few other applications in my all right. So this is my equation, let's say equation number 6. Now what equation number 6 tells us is that the sum of exponents, look at the right hand side, the sum of exponents is equal to the sum of Dirac delta functions. And also observe that in the real that there is in the exponent you have 1 over p, whereas in the Dirac delta functions you have p. Now if I look at equation number 6 and I compare it with the Fourier transform of the Dirac delta pulses that we've already found, where do we have that? We have that over in equation number 1. So this is, let's call this equation number A. So equation number A, the Fourier transform of the lattice, one-dimensional lattice, is given by n e minus I k n a. This is my equation number A. Now, can you compare equation number 6 and equation number A and write this exponent in terms of Dirac delta functions? Can you work backwards? Of course you can do that. And if I were to look at equation number 6 and equation number A together, then my Fourier transform of the lattice will become equal to 2 pi over A Now I give you two or 3 minutes just to derive this. So look at equation number A. I would like to express the sum of exponents as a sum of Dirac delta functions. And the way I do that is I use equation number 6 to perform this transformation. So can you use 6 to derive this equation number 7? So just on your own, please, I give you 2 minutes just to see if all of this is making sense. So the summary is here is that if I have in the real space, I have a sum of Dirac delta functions, which is my direct lattice, and the spacing between these lattice points is A. Then I were to take the Fourier transform of this direct lattice, I will once again get a sum of Dirac delta functions. And the magnitude or the strength of each Dirac delta function is now slightly different. It's this 2 pi over A here. And the spacing between these points is now given by not by A, but by a factor of 2 pi over A. So this is the reciprocal lattice. So the Fourier transform of the direct lattice is the reciprocal lattice. Got it? Any questions about this? So the reciprocal lattice is simply the Fourier transform of the direct lattice. And if I were to extend this to 3 dimensions, in 3 dimensions, the concept is straightforward. So if I have a 3-dimensional lattice, so now which is represented by the variable L, and I take the Fourier transform of the 3-dimensional lattice, I would get, instead of getting a 1-dimensional Dirac delta function, a series of 1-dimensional Dirac delta functions, I would get a 3-dimensional. Let's represent this by delta 3, and now I have to replace this vector, this simple scalar variable k by a vector, which is now my k vector. And if you recall, these n minus 2 pi, n into 2 pi over a is just the length of the reciprocal vector. And when I'm talking about 3 dimensions, this becomes the reciprocal vector itself, which I'm denoting by g. Okay. And I have to sum up over all of g's. In equation number 7, I was summing up over all of the reciprocal lattice vectors in 1D, which was 2 pi over a, 2 into 2 pi over a, 3 into 2 pi over a. These are just different reciprocal lattice vectors in a one-dimensional reciprocal lattice. In 3 dimensions, I simply replace this by the reciprocal lattice vector, the generic G. Okay, and I sum up over all possible G's. And I have to do the proper normalization as well, which in 3 dimensions become 2 pi cube over the volume of the unit cell in the real space. So this is the Fourier transform of the lattice. So the Fourier transform of the lattice is the reciprocal lattice. The reciprocal lattice exists in the reciprocal space. So this is such an important point. I would like to write it down. The Fourier transform of the direct lattice is the reciprocal lattice. And what I've written above this is just the mathematical formulation of the reciprocal lattice. Dirac delta functions in K space. This is my variable. K is my variable because the reciprocal lattice lives in a new space, which is now the reciprocal space or the K space as it is called. But only certain points glow, just as in a grid, as in a lattice. The reciprocal lattice is also a lattice, but in the K space. And only points which are separated out by G's act. So if I were to draw the reciprocal lattice in 3 dimensions, so this is net. Sorry, my pen is somehow. I think my screen is just giving up now. So only points which are separated from some origin by G's. So these are my G's. These are my G vectors. Only these points have a Dirac delta function existing in those points. So this is what a lattice means in the reciprocal space. So the reciprocal lattice is the Fourier transform of the direct lattice. Now, in order to find the Fourier transform of the crystal, we now need the Fourier transform of the basis. Okay, because if you recall, the Fourier transform of the overall crystal is a product of the Fourier transform of the lattice with the base. So this is what we are interested in determining. This thing. We found out the Fourier transform of the lattice. Now we need to find out the Fourier transform of the basis. Then we multiply the two together, we'll find the Fourier transform of the crystal. And I'll show in the next class that this is equal to the diffraction pattern itself. Okay. In fact, I take this modular square of it, it equals the diffraction pattern. So now the key idea is that we found out the Fourier transform of the lattice that is equal to a sum of exponents, which is equal to a sum of Dirac delta functions. And we've proven this using the concept of the Fourier series. Now, what we would like to do is we would like to find out the Fourier transform of the basis. So let me just start this discussion and I'll give some real examples in the next lecture. So So suppose I have a basis. Now the basis can be an atom. It could be a collection of atoms. It could be any motif whatsoever. Suppose the Fourier transform of this basis. Now let's go back to one dimensions. Suppose the Fourier transform of the basis looks like this. Okay, one atom, I find out its Fourier transform. This is what it looks like. Now in 1D, I have a reciprocal lattice, which is given by Dirac delta pulses. So this is my Fourier transform of the basis. This is the Fourier transform of the lattice. In 1D, I'm back to 1D. This spacing here is 2 pi over a. Now what I need to find the Fourier transform of the 1D crystal, I simply multiply these two together. Now everywhere I can use the sampling theorem again. Everywhere do I get 0? I only get non-zero values. Only get non-zero values when a Dirac delta function coincides with the basis. So only these points in the reciprocal space become valid. The product of this Dirac delta function with the basis Fourier transform is 0 because there's no Fourier transform. Everywhere else do I have 0. I'm really sampling the basis function at the points at which the reciprocal lattice vector exists. Now this rings a bell with the evolved construction. So what I finally, if I were to multiply the two functions together, I will get functional values using the sampling theorem of this kind. So I'm picking up the amplitude of this B function at precise points, and those points correspond to the reciprocal lattice points. So my final product, CK, will look something like this. And this is in fact equal to, if I take the modulus square of this. So if this C, by the way, can be a complex function, as I'll show you with some examples in the next lecture. C can be a complex function. If I take the modulus square of this pattern, and by the way, this is the reciprocal space here. Everything is in the reciprocal space, and this is 2 pi over a. So if I take the modulus square of this function, I get the intensities of the X-ray beams, scattered X-ray beams. So the Bragg's law gives me the directions of these scattered X-ray beams, and this Fourier formulation gives me the intensities of the scattered X-ray beams. And the intensities are given by the square of a function. That function is the Fourier transform of the crystal. And the Fourier transform of the crystal can be found by sampling the Fourier transform of the basis at precise points which are equal to the reciprocal lattice points. Okay. Now in the next lecture, what I will try to do is I will try to use this formula. I need to find out the Fourier transform of the basis, by the way. I can use simple arguments from wave mechanics to find out the Fourier transform of a collection of atoms, which are really scattered X-rays are really coming out from the electron density. So I need to find out the Fourier transform of the electron densities of each motif, of each basis. And then I know that I need to sample them at the reciprocal lattice points, and that will give me the strength of the diffraction peaks. I already know what directions the diffraction peaks are coming out in. All right, so this finishes off my lecture for today. I'll be happy to take some questions if there are any.
Sir, I have a question regarding the Bragg representation जो हमने last class में की थी.
जी जी.
तो सर can I annotate on your screen यहाँ पे मैं draw करके आपको दिखा दूँ?
जी प्लीज. मैं आपको होस्ट बना दूं?
नहीं सर, मुझे इसी तरह मैं draw कर सकता हूँ.
करें आप प्लीज.
तो सर here we had a direct lattice जिसमें हमारे पास planes थे और हमारे पास कोई एक्सरे बीम आ रही थी दैट वाज फॉलोइंग ऑफ एट सम एंगल थीटा और रिफ्लेक्ट बैक कर रही थी यहाँ से भी, और सर सम अदर बीम जो कोई और आ सकती थी वो नीचे वाले प्लेन पे भी जाके इंटरसेक्ट करके विद एन अदर एंगल जो कि फिर से थीटा है, तो ये भी इस तरह से रिफ्लेक्ट बैक करती थी और हम यहाँ से इसका फेज वगैरह देख रहे थे। सर माय क्वेश्चन इज कि अगर यहाँ पे से ये जो बीम है यहाँ फॉल कर रही है तो वी ऑल्सो हैव एन एंगल थीटा हेयर, तो यहाँ से ये रिफ्लेक्ट बैक क्यों नहीं कर देती और ये नीचे वाले प्लेन्स पे जाती कैसे है इफ यू आर गेटिंग अ परफेक्ट रिफ्लेक्शन हेयर?
वहां से भी रिफ्लेक्ट करेगी, कोई मुजायका नहीं, वहां से भी रिफ्लेक्ट करेगी, कोई प्रॉब्लम नहीं है। असल में द ब्रैग फॉर्मूलेशन इज really a model. Okay, it describes how diffraction occurs. It does not give you the complete physical interpretation. So it is a model. There is another model which is called the Lowey's model, which allows us to give a more general view of scattering, and then we can show that the Lowey formulation is completely analogous. It coincides with the Bragg's formulation. Okay, and the Lowey formulation doesn't talk about X-rays reflecting. It talks about X-rays scattering from certain angles. So in this particular case, if the Bragg's model were correct, and indeed it is correct, there will be reflection from every other point inside the plane. But X-rays also have a certain penetration. They are not just merely surface phenomenon. They have a penetration, although the penetration is much deeper than electrons, of course, but they do penetrate inside they don't remain on the outer atomic surface. They do go inside uh, the solid as well.
Okay sir, got it, thank you.
Okay, so remember that the Bragg's formulation is a model. If I were to look at the Larvae formulation, let me give you an idea of what the Larvae formulation is. So the Larvae formulation is that a beam comes in vector S naught and it is scattered S. It's not reflected, it's scattered. Okay, and then there is a neighboring atom at a distance A. Neighboring atom at a distance A. The beams are all coming in at S naught, scattering off at S. Okay, now we can find out the phase difference in this particular way. Now, this formulation does not talk about reflection. The reflection was a clever conjecture of the Bragg father and son, and it works. So, but the Larvae formulation does not talk about reflection, it talks about scattering. So, if in this particular case, I were to find out the OA path difference BC, I will need to find out BC minus OA, and I can define this vector here, the A vector, and it turns out that if I look at this scheme, S minus S naught dot product with A has to be equal to an integral number of wavelengths. This becomes the Bragg formulation. Okay, so if this were true, then the beam will be scattered off at an angle S. This is called the Larvae formulation, and it turns out that this is exactly coincident with the Bragg formulation. I can just replace A by the reciprocal lattice vector, keeping in view the magnitude, which is 2 pi over A, and you get the Bragg formulation back again. So this Larvae formulation is not talking about reflection, but it turns out to give you the same mathematical results as the Bragg formulation. Okay, so the Bragg formulation is a model. It models scattering as reflection, like reflection occurring from a perfectly reflecting mirror. Okay, any more questions? So by the way, I probably give this as a homework. You can actually derive this equation that I've written over here. S minus S naught dotted with A equals nx lambda. Probably give this as a homework. And likewise, I have S minus S naught dotted with another lattice vector B will give me some other integer ny and lambda. And you can find out later that these nx and y's, they are equal to h, k, and l of these particular planes. All right. Any more questions? So in my next lecture, what I would like to do, I would like to find out the Fourier transform of the basis. I combine the Fourier transform of the lattice with the basis, multiply the two together. I've already shown graphically or intuitively what this means. And then from the output, I would like to find out what the diffraction intensities are. And I will see that for certain Bravais lattices, certain intensities are always zero. They never show up. These are called the systematic absences. All right, friends. So thank you very much. Do submit homework number 3 as well in time. I think that is due today. You can submit it by the midnight. And I'm also preparing homework number 4. And then next week, we're going to start our discussion on electrons inside solids. And we're going to start talking about the band theory. All right, friends. Thank you very much.
Okay, sir.
And Khuda Hafiz.